Hello. So this is the first lecture of chapter 2, which is section 2.2, and it is about introduction to limits using some calculations, some computations. So we'll start by seeing how to obtain the limit using calculator. So we take the example of the function f of x equal to x squared minus x plus 2. Okay, and we want to get the limit of this function when x is near 2 here. Okay, so basically you need to take some values close to 2. That means I will take, as we will see later, x equal, for example, 1.9. This is close to 2. If we want to get closer, then I will take x equal to 1.99. And closer and closer, 1.999, and so on. And here you see that we took some values close to 2, but less than 2. Okay, and I will need to do the same thing, but x greater than 2. So I will say let's x equal to 2.1, for example. Okay, if I want to get closer to 2, then I will take x equal to 2.01. Closer again, so 2.001 and so on. Okay, and I will substitute these values of x and these ones in the function f of x, and I will make like conjecture. I will say that this is my conclusion for the limit. So we will see here this table of values, and clearly these are the x's and these are the y corresponding, and we see in particular the last one is close to the last one here, and we can conclude that the limit is equal to 4, in fact, because it's not the value here is not exactly the limit, it's approaching the limit, but clearly the limit will be 4, the number 4. Okay. See here in the graph how to find the limit from the graph. So if we are concerned with the limit of f of x when x is approaching 2 is equal to what? Then I will go to the graph and put my x equal to 2. You remember that in the limit, we don't take x equal to 2. In general, x is not equal to 2, but we take it close to 2. Here in the graph, just this is the manner in the graph. So you take x equal to 2, and you see when you are close to 2 to the right, close to 2 to the left, this point, the 2 points that I put in the graph, they are somewhere here and here. And if you get closer and closer, this point and this point will go to the same point here, and this is exactly the value of y of this point is 4, and this is exactly the limit. So we may conjecture that the limit here is equal to 4. Okay? And this is what we conclude in this page. Now, here is the rigorous definition of the limit. We say that limit of f of x is equal to L when x is approaching a. This is the notation for the limit. We can also denote this by f of x approaching L as x approaching the value a. And here a is a number, a real number. Okay, so we will see later when we talk about infinity when x is approaching infinity. This is another stuff, we will see it later. For now, a is a real number. So we take, by the first method, by calculation, we take some values of x close to a but not equal to a, from right, from left, and we conclude. Of course, this is the first definition, but later we will see that we can use some rules for the limit. Okay, here is again a notation. And in the graph, we will have the following situations. Here, we see clearly that the function is defined at A. It has the value L here. And when we see the limit, so right, left, they meet at the same point, which is L, so the limit is equal to L. In the next graph, graph number B, again here the x approaching A, we see here that the function is defined on L, but it is different than this value L. Although this difference, the limit is all the time taking right, left, they meet. If they meet at a point, this point is the limit, okay? So whatever the value of the f of A, the limit is something different. You look at the right, left, if they meet on the point, on the same point, then this is the limit. If they don't meet, we will see that the limit does not exist, okay? The situation number C, the graph number C, you take A, although f of A does not exist, is not defined here, okay? But the limit still exists and it is equal to L. Same value here is equal to L because they meet, right, left, they meet, so it is equal to L. So the notion here, what we can learn is the notion, the concept of the limit is sometimes totally different from the value of the function at the point. Look at this example. Guess the value of limit x minus 1 over x squared minus 1 when x is approaching 1. Okay, no. So far, we don't have any other tool. We only have the calculator to do that. So we will take some values of x close to 1 from the right, from the left, and then we will conclude. Look at what we will get if we take some values. Here, clearly, the last one is the most closer to 1, and here also same. So for f, we are very, very close of the value. Let's say this is our conclusion. So the value will be 0.5. That's the limit. This is the conjecture. So limit of f of x when x is approaching 1 is equal to 0.5 because we find that left values, right values, they meet on the point 0.5. So this is the limit, in fact. Okay, again, with the graph now, we will see that the limit of the function g of x, that we have the graph in figure 3, we do right, left as usual. This is the point 1, and point to the right, point to the left. They meet, right, left in the graph, they meet on the same point, and this is the limit, which is 0.5. And it's totally different from the value of f of 1, which is equal to 2. Okay, so be careful here. It's not all the time the value of the function at the point A. So clearly, here you see that f of 1 is equal to 2, but the limit is 0.5. Now we arrive at the definition of one-sided limits. We called it previously right-left. So we will make a sense to this definition, okay? Let's take this example, the function h, for your information. This is called the Heaviside function. Okay, it's not important, but you can, at least for general culture, you can remember this name. Maybe later you will need this. What is the definition of h of t? It is equal to 0 if t is negative. So this is the expression number 1 for the function h. And it is equal to 1 if t is non-negative. This is expression 2. Okay? So we will remember of 1 and 2 when we need that. Now we look for the limit of h of t when t is approaching 0. Okay? So we will see t approaching 0 from the right and t approaching 0 from the left. When we say right, that means t approaching 0, but t is greater than 0. Okay? And when we say left, t is approaching 0, but t is less than 0. Okay? We will call right by, for this case, 0 plus and left 0 minus. So these are the one-sided limits, plus and minus. And now what's the difference in terms of limit? And by the way, the one-sided limits exist all the time. So if you look to the right limit, to the left limit, separately, they exist. Okay? When we can talk about the limit does not exist, when right and left, they don't meet at the same value. They are not equal to the same value. That means that the limit at the point does not exist. Okay? And here you see for 0 plus, because I am greater than 0, then I will use expression 2. And what is the value of the h for expression 2 is equal to 1. And for the left, I will use expression 1. And for 1, I am 0 minus. Then I conclude that my limit is equal to 0. So you see here that the limit to the right is equal to 1. Limit to the left is equal to 0. They are not equal. So the conclusion is the limit at 0 does not exist. But for the one-sided limits, they exist. Okay. Here is the definition of the limit to the left-hand limit of f of x. So basically, it's the same, just you put x approaching a minus 1. That means x close to 1, to a, sorry, but x is less than a. So even if I take the table of values, I don't take x greater than a. Just I will take x less than a. Same, similarly for a plus. Okay. So in terms of graphs, you will see that when it is a plus, when it is, let's start with a minus. This is a. So approaching a minus, that means x is somewhere here. I cannot take this side. And when I say a plus, this is my a. So I am somewhere here. Okay, but I cannot take the left. Okay. Now you see in the graph, for example, for a plus, when I am close to a, I will go to the graph and see where my graph is going when I am to the right of a. Same for the left. I will take a point to the left and I see where my graph is going for a minus. Look at this definition now. Our theorem, we have limit of f of x is equal to L when x is approaching a, if and only if the two one-sided limits, a plus and a minus, they are equal to the same value. Okay, so if I find this and this, then I can conclude this. Okay, good. Let's see this example to find some limits. Here I will explain how to find them. So for example A, I'm looking to the limit of g of x when x is approaching 2 minus, that means that I am to the left of 2. Here is 2, the point 2. I am to the left, so I am somewhere here. Project this in the graph and take the limit. Clearly, my limit will be equal to 3. Number B, for 2 plus, so I am, let's erase this. Okay, then I will take the 2 plus here. So I am close to 2, but here, somewhere here. Make the projection on the graph and see where I am going when I approach 2 is the value 1. So it is equal to 1. And from A and B, we can conclude that limit of g of x when x is approaching 2 does not exist. Okay, I will make this short to say that the limit does not exist. I will write it for the first time like that, then later you will understand that D and E does not exist. Okay, good. Okay, so now going to the question C here, limit of g of x when x is approaching 2, already done in my remark here, so this does not exist. Limit of g of x when x is approaching 5 minus, that means that I am close to 5, but I am on the left to 5. So clearly, my limit will go to 2. So this is equal to 2. And even for the right, it's equal to 2. So since right, left, they have the same value, 2, 2. So my limit is equal to 2. And we are done till example 7. Okay, just I put the conclusions here. We know that g of 5, of course, is not equal to the limit 2 in this example. Look at this, try and check. We will do the same, almost same questions for the function f. So we want to find limit of x when x is approaching 1. So I will do right, left to 1, and then find the limit. Here is 1, and the value 1. So right, left, they meet at 3. Okay, so the limit is equal to 3. Question B, limit of f of x, x approaches 3 minus. I will change the color because the graph is in red here. Maybe it's better to use another color. So 3 minus, that means my x is 3 and I am to the left. So where the graph is for 3 to the left, here. Okay, so let me repeat this. Okay, and I am approaching the value 2, so my answer is 2. However, for 3 plus, I am close to 3, but this side, so it is equal to negative 2. X approaching 3, my conclusion comes here for 3 using B and C. You see here that this is minus 2 and this is 2. So clearly the limit does not exist here. F of 3, from the graph, I see that f of 3 is equal to 1. So the situation here is that f of 3 is defined equal to 1. The limit to the right is not equal to the limit to the left. So the limit does not exist, although the function is defined at the point 3. Now going to f, limit x approaches minus 2 minus. That means that I am close to minus 2, but to the left of -2. So I am here, okay? Projection on the graph that gives me the value -1. And since also in the plus here, they meet at the same point, so this is -1 also. So from f and g, the limit to the right equal to the limit to the left. That means this is equal to -1. What is f of -2? It's totally different. You see here, f of -2 is equal to -3. So we can conclude from this try and check example that the limit sometimes does not have any relationship with the value of the function itself. But we will see that in many situations, they will be the same. But it is not necessarily the case for all the functions. Okay. Let's move now to the infinite limits. For a function f of x, we have the limit x approaches a equal to infinity. What does mean this? So when you approach a finite number a, the function is becoming very large, infinity. And we'll see later that it may be minus infinity. The same phenomena will happen. So what this kind of function is? You remember, for example, okay, we saw in semester 2 what we call it the tan function. Okay, tan function is somehow like that. Okay, going to infinity when x is close to pi over 2 or minus pi over 2 on the other side. So this is y equal to one of the branches of y equal to tan x. So here is an example of this situation. X approaching a value pi over 2, and the f of x is going to infinity. Okay, so here is another illustration for the graph of function f that it is going to infinity when x is approaching a number a. Same situation here, but we are going to minus infinity in this example. So in conclusion, it is whether plus infinity or minus infinity for these infinite limits. Okay, so same definition here for minus infinity. As an example, you see here that when you take x approaching 0 and you compute the limit of -1 over x squared, the x squared here, since x is close to 0, it will be close to 0 plus. Okay, so 1 over 0 plus, it will be infinity somehow. Okay, it's like infinity. With the minus, so it's minus infinity. That's why this limit is equal to minus infinity. So similar definition will be for the one-sided infinite limits. For a minus and a plus, it can be plus or minus infinity. Okay, so same rule. And here some illustration. Now we arrive at definition 6. We say that the line x equal to a, and if you remember, this line is in fact a vertical line. When you take a vertical line like that, the equation of this line is x equal to a. Okay, so we say that x equal to a is a vertical asymptote of the function f of x, or the graph of f of x, if one of the situation happen here. It suffices to have one, just one. Okay, so whether the limit when x approaches a is equal to infinity or minus infinity, these two situations, or also limit to the left equal to plus or minus infinity, limit to the right, okay, plus or minus infinity. If one of these 6 conditions happen, then we say that x equal to a is a vertical asymptote for f of x, for the graph of f of x. Look at this example here. We have to find the vertical asymptote of tan x. We remember that tan x is sine over cosine. And we have, since we have here denominator cosine, so probably this will have a problem when cosine x, not probably, it's sure, we have a problem when we have cosine x equal to 0. But when cosine x is equal to 0, remember, at least the first value that we know for each for which cosine is equal to 0. Remember, if we take a point here, the x is the cosine and the y is the sine. This is the 0.10, and this one the 0.01. So clearly here is the cosine of this angle, which is pi over 2. So cosine pi over 2 is equal to 0. But not only the only point here. If we go to the next one here, cosine 3 pi over 2 is equal to 0 as well. And so on, since cosine is 2 pi periodic, so it's of the kind pi over 2 plus k pi. All these points, this form, will have cosine equal to 0. Okay, this is my star. All these points have cosine equal to 0. So I need to remove these points from the real number sets, r minus these points. And clearly, we will see that the graph of the function tan will have this vertical asymptote when x is approaching one of these points in star. Okay, as an example here, we can work on the point pi over 2. So from the right, the tan will be equal to minus infinity. And from the left, it is equal to plus infinity. Why this? Because we have the graph of the function tan. Let me see if we have the graph here. You see here that if here the point pi over 2, if I am to the right, then the graph is going to minus infinity. If I am to the left, then I am going to plus infinity. Okay, that's why I have these two conclusions here. Okay, and the same phenomena will happen for any point like what we wrote before, pi over 2 plus k pi with k in z. All these will be vertical asymptote for the function. So from these two limits, I can conclude that pi over 2, x equal to pi over 2 is a vertical asymptote. You remember this for the vertical asymptote, we have infinite minus infinity. So x equal to pi over 2 is a vertical asymptote. In fact, you need just one. Left or right, you can conclude that x equal to pi over 2 is a vertical asymptote. But of course, here you need to find both of them, since sometimes the limit to the right is not equal to the limit to the left. So you may have different vertical asymptotes. Okay, so remember this, please. Not all the time that the right and left, they have the same value in the limit. Okay, so we saw this graph. Now we will do the try and check example, and we will finish by this. So look at the function in the graph below, and we want to confirm or find from the graph the following information. Limit f of x when x is approaching 3. So here we didn't precise right and left, so I have to see right and left to conclude the limit at 3. 3 is here, you see, and from the right, the graph is going to infinity. From the left, the graph is going to infinity. So the limit is equal to infinity. If you find that right, left, they are different, then right limit does not exist. So sometimes you find that right to 3 is plus infinity, right to left to 3 is minus infinity. The conclusion that the limit does not exist. But x equal to 3 still is a vertical ascent. This is another thing, okay? Limit f of x when x approaches 7. Here is the point 7. Okay, so right and left, you see the graph, and clearly it is equal to minus infinity. Limit f of x when x approaches minus 4. Minus 4 is somewhere here, so I have, this is minus 4. So clearly, to the right and to the left, the two graphs, the two parts of the graph are going to infinity, to minus infinity, so the limit is equal to minus infinity. Then we will look to minus 9 left and minus 9 right in example D and E. For D, I will have to the left, so I am going to plus infinity. And to the right, here, I am going to minus infinity. Now, in F, I will conclude all the vertical asymptotes using the results that I found already. So clearly, x equal to 3 from A, x equal to 3 is a vertical asymptote. This is the answer for F. Then x equal to 7. Since I found minus infinity. X equal to minus 4. And x equal to minus 9. So 1, 2, 3, 4 vertical asymptote that we found in this example. And by this, the lecture 2.2 is finished. Thank you.